Hello, welcome to Week 10, Lecture 2. We're going to talk about gravitational potential energy. This is Chapter 14-6. So, gravitational potential energy, then we're going to do a sample problem, and then potential energy of a many particle system. So before we jump into the gravitational potential energy, we want to confirm that gravity is a conservative force at this scale. So we have particles capital M and lowercase m, and little m is going to move to eventually be closer to big M on three different paths. Okay, so path 1 here, I will highlight it there, and there to point B. So the particle moves over to A, or the mass, and down to capital A and over to B. So the only motion that does any work in path 1 is going from little a to big A, because going from big A to B doesn't change the distance between the two masses. So no work is done in that motion. For path 2, we go along this way to capital B and then straight down to lowercase b. And so in this case, the motion that goes kind of along this path up here to capital B, that doesn't do any work, because the force and the displacement are perpendicular to each other. So no work is done in that motion, but then when it goes from capital B to lowercase b, then work is done. And finally, path 3 is kind of zigzag. It goes from C down to D, over to E, down to F, over to G, and then down to H. And so again, here, the only motion that does work is the motion in the direction of the mass here, because throughout the force on lowercase m is pointing toward capital M. And so only motion along that, either parallel or anti-parallel, does work on the system. So I obviously am not going into as much detail on this version of proving we have a conservative force than I did previously, because we did actually already prove that gravity was a conservative force. But I wanted to make sure you saw this in this new format of thinking about gravity. Okay, so now we're gonna work this situation out to find the gravitational potential energy of the system. But to do that, we are going to need to write some things out. So just a moment. Okay, so we have two masses here. Again, lowercase m and capital M. And we're gonna move the smaller mass from point B to point A. 1 second. Sorry, we're moving the smaller mass from point A to point B. So closer to the bigger mass and then farther away. And we want to find the work done by the gravitational force in that motion. So we need to start with integration. So work from A to B equals the integral from A to B of the force dotted with dr. So as you can see here, force is going to be in the direction toward the other mass. But then since we're moving outward, dr points in the opposite direction. So the dot product of those is going to give us a negative. So then we're going to write this as negative A to B f dr. And then we can plug in our equation for F, so the force of universal gravitation. So negative. And in this case, I'm gonna switch from A to B here to RA to RB. That's an A. So that we are looking at the specific radius. And then G, capital M, lowercase m, over R squared, dr. But then G, M, and M are constant, so I'm going to pull those out. Negative G, M, M from RA to RB, 1 over R squared dr. And then the integral of 1 over R squared is negative 1 over R. So negative 1 over R from RA to RB. And we can plug those in. And we get negative GMM times 1 over R. I'm actually going to distribute this negative sign and do a little rearranging because of that. So then it's 1 over RB minus 1 over RA. Because distributing this negative sign here, giving that a positive. So this is the work done to move the smaller mass from a distance RA to a distance RB. The other thing we know is that the change in potential energy of a system is negative the work done. So this is final minus initial. Final is B. Oops. Initial is A. And that equals negative work done. Which gives us negative GM 1 over RB minus 1 over RA. We could also write that as again distributing the negative sign, so just switching these two around. So then we get 1 over RA minus 1 over RB. Either way. So that is our equation for the change in gravitational potential energy in moving from A to B. But then let's think of another situation where we instead are starting at a radius R away from the mass and then moving out to a distance of infinity. So U of infinity minus U of R. So this is final minus initial. And this is, if we write it this way, so we switch the position of them around so we don't have a negative sign out front, we get G, capital M, lowercase m, 1 over R minus 1 over infinity. But 1 over infinity is 0. So, and the potential infinitely far away is also 0. So what we end up with is the potential at a distance R away from a mass is GMM over R, negative GMM over R. Okay, now we're going to do an example problem. So we have a satellite orbiting at an altitude of 2 Earth's radii above its surface. It launches an equipment canister of mass lowercase m toward the Earth's center with a speed of v initial equals 525 meters per second. With what speed v final does the canister enter the Earth's atmosphere, which is a distance of 100 kilometers above the surface? So let's write out a few important things. So the initial distance is going to be 3 Earth radii. And that's because we have one Earth radii for going from the center of the Earth to the surface, plus another 2 Earth radii for how far it is above the surface of the Earth. And then the final distance is the radius of the Earth plus this h, which is 100 kilometers. Let's see, I think that is sufficient for now. So we're just going to solve this with conservation of energy. I just gave you the equation for gravitational potential energy. So let's use it. So the initial gravitational potential energy, initial kinetic, equals the final gravitational potential energy plus the final kinetic. None of these are zero, so unfortunately we can't just get rid of stuff, but that's okay. It's not too bad, I swear. So negative g mass of the Earth is this capital one, little m. And then this is initial, so it's 3 radius of the Earth. And then we add 1/2 mv initial squared for the initial kinetic energy. And then we have the final potential, gm over radius of the Earth plus h plus 1/2 mv final squared. So first thing we can do is just cancel out these masses of the, what is it called? Equipment canister, because it's in every term, and we can just cancel that out. And then because what we want to find is V final. So let's try and get that by itself. So let's add this term to both sides. And in doing that, I'm going to factor out G capital M. So we end up with 1 over radius of the Earth plus h minus 1 over 3 times the radius of the Earth. And then we add 1/2 v initial squared. This equals 1/2 v final squared. And if we just multiply both sides by 2 to get v final squared by itself, we end up with 2gm times 1 over radius of the Earth plus h, minus 1 over 3 times the radius of the Earth plus v initial squared. And that's going to give us v final squared. Okay, I'll plug in the numbers. They're big numbers, so it's not going to look nice. So 2 times 6.67 times 10 to the negative 11 meters squared per kilogram squared times the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. And then we have, let's see, the radius of the Earth plus 100 kilometers, yes, is 6.47 times 10 to the 6 meters, minus 1 over 3 times 6.37 times 10 to the 6 meters. Finally, we add 525 meters per second squared. And we end up with V final squared equals 8.37 times 10 to the 7 meters squared per second squared. Obviously, we generally don't just want the squared. So if we take square root of that, we get the final velocity equals 9,149 meters per second. So super fast is the answer there. And really quickly, just review of what we did. First, just established what our distances are. So we have something going around the Earth, and it has this initial position from the Earth, which is our initial, and then it ends up at a final position, our final. And we wanted to know what the final velocity was. And we used energy, conservation of energy. And so we used conservation of energy, solved for V final, and found this value. Okay, now I want to derive something for you. So we're working from a situation where a projectile is fired straight up from the surface of the Earth, and we want to think about what would be necessary so that its final kinetic energy and gravitational potential energy are 0. So this is initial kinetic plus initial potential, final kinetic plus final potential. But I just said this side is going to be 0. This side isn't. So 1/2 mv initial squared plus g mm over r Earth squared, because that's just, well, maybe I'll just leave it as r, so it can be any starting point. Oh, sorry, it's not squared. That equals 0. Missing some things. Negative sign. There we go. Now, we want, so if we're assuming it's fired straight up from the surface of the Earth, well, what velocity would give us enough kinetic energy to escape the Earth's gravitational field? So we're going to add this term to both sides, and then we are going to divide both sides by, or multiply both sides by 2 over m. Let's say that instead. Multiply 2 over m. So we end up with the initial squared equals g m over r times 2 over m. Those m's cancel, lowercase m's cancel out. And then we can also take the square root of both sides. So we end up with velocity initial is the square root of g times capital M over r. Oh, sorry, 2g times capital M over r. Let me just rewrite that so it's clearer. What I get for putting the 2 on the other side. 2gm over r square rooted is the initial velocity necessary for this projectile to escape the Earth's gravitational field, and this is called escape speed or escape velocity. Okay, now we're going to look at the potential energy of a system of particles. And an important thing to note is, and this is weird, this is a heads up, but how this works is the potential energy of a system of particles is equal to the work done by an external agent to assemble the system from infinite separation. So, for example, with these 3 particles here, we would first bring mass 1 from infinitely far away, but since none of the other particles are there, it doesn't take any work to bring that guy in. But then when we bring in mass 2 from infinitely far away, work is done in that case because there is the gravity from mass 1. And then finally, if we bring in mass 3, it experiences a gravitational force from mass 1 and mass 2. So work is also again done to bring it in. So I'll show you what this looks like. Work to bring in mass 1 is 0 because nobody else was there. Work to bring in mass 2 is g m1 m2 over the distance between them once we stop bringing them in. And then for the work done to bring in mass 3, it's just the work done by the gravitational force from each of the other masses. So gm1 times m3 over the distance between those not squared, plus gm 2 times m3 over the distance between those. So what we end up with is the gravitational potential energy and the work done to assemble these masses together is negative times our negative of g m1 m2 over r12 plus g m1 m3 over r13 plus g m2 m3 over r23. So this is, I know it's a weird concept to be like, some external agent has to bring this mass in from infinitely far away. But it is something that will come up also again in electricity and magnetism. So I thought it would be useful to at least introduce it now before you see it with other complicated topics. But the main idea is, in order to know the work done to form some sort of system, you have to find the work done to assemble it piece by piece. Yeah. So that is everything for this lecture. Hope you have a great day.